I'm working at home. Well, it's 2 minutes past 12 on Saturday here in New South Wales, and I'm working at home. If a fire started in our house, how much time would I have from the start of the fire to discovering the fire to being able to leave the home safely? Or there's only one way that you can really answer those kinds of questions, and it's like the ultimate fire science experiment. You buy a house and you burn it down. And that's a pretty kind of expensive experiment to do and not very reproducible. So when fire engineers or fire scientists are trying to understand how household materials like books or sofas or clothing will ignite and combust, they have to do small scale experiments. And today's talk is about a very simple equation that's actually used in fire engineering to analyze experimental data. Can your student solve this differential equation? Now, I don't mean this differential equation when I put numbers into the differential equation. I mean this differential equation when there's no numbers and there's parameters. If your students can solve this equation, then we can take a step into the world of fire engineering because this equation is what's used to analyze experimental data. So yes, the ultimate experiment is to burn down a house, but a simpler experiment is abstracted in this figure. I've got some sample, and the experiment's very cleverly designed to ensure that there's a uniform heat flux occurring over the top surface. And the consequence of assuming that there's a uniform heat flux is that heat transfer is going to be one-dimensional in this direction. Now, that gives a PDE model, and PDEs are great, but it's a little bit complicated. So we can make life simple because we're going to assume that our sample is thermally thin. And thermally thin means it's sufficiently thin that there's no temperature profile across it. So I can talk about a homogeneous temperature. There's just one temperature for this material. So yes, ultimate experiment. It's pretty exciting. You burn a house down. Why am I talking about radiative heating? Because in most fires, radiation is actually the main mechanism for transferring heat from the fire front to ahead of the fire front. Conduction and convection are not important. This kind of experiment started in the 1950s by the US military. And more recently, I suppose not that recently now, but in 1982, at the NBS, they invented a piece of equipment called the cone calorimeter. We need to know absolutely nothing about it, but it's a standard tool to analyze the burning behavior of small samples. And from our perspective, the most important thing is the fact it gives a uniform heat flux across the sample. Complicated as you like. You can put more physics into it and more chemistry into it. You can get very complicated models, but the simplest model is to ignore all the chemistry and to assume that your material is chemically inert until it reaches a critical surface temperature and then it ignites. So here's our equation. This is the equation we need our students to be able to solve. So perhaps I'm in an unusual position because I'm teaching a second year subject for mathematics students, and I've got 6 weeks when I teach heat transfer. I'm using this book by Barnes and Fulford, and if you don't know it, it's really good. Case studies using Maple. There's lots of really cool case studies, and a lot of the models are just single differential equations or couple differential equations. So you don't need to use Maple to look at it. So my students are actually learning how to derive the mathematical equation from a word problem explaining the experiment. But your students probably aren't doing that. So you could start by giving them the equation, but it looks a bit intimidating, this equation, because there's a lot of symbols in it. Now, before I go on to simplify the equation, let me just say what the terms are. Now, the left-hand side is the rate of change of heat content in my sample that's been heated up. And the first term is the rate of change of heat content due to convective heat transfer between the solid and the atmosphere. And the third term is the rate of change of heat content due to radiative heating. If you've used this book, there's a problem in here, which is the water tank problem, which people have talked about at previous meetings. And this model is actually identical to the water tank problem in here. So what my students, they don't like this equation. There's too many symbols in it, and they rewrite the equation to make it look simpler. So some of them like to rewrite it in this way, or some of them like to rewrite it in this way. And by defining your own notation, you can make the equation look nice and simple. I think that this is actually the best way to do it, and I'll explain why later on. But this is a very appealing way to rewrite the equation. So maybe if you were teaching first-year students who are doing a differential equation subject, maybe you wouldn't give them the horrible-looking equation. You might rewrite the equation for them and give them the simpler equation. All right, so it's a first-order separable equation, and we can solve it. And in differential equations, that might be the end of the game. We've solved the differential equation. But in mathematical modeling, solving the differential equation is not the end of the game. And it's not the beginning of the end, but it might be the end of the beginning, which I think is a quote from Winston Churchill. So we've got our solution, but we want to say something about the experiment using the solution. Now, the sample ignites when the temperature reaches the ignition temperature, and that occurs when the time reaches the ignition temperature. So it reaches the ignition time. So, I can rearrange the equation to get this form. Now, I'm going to tell you something now that you might not know, but it's going to be immediately obvious to you once I've told you. If I want to ignite any material, there's got to be a sufficiently strong heat flux on it. If the heat flux is too low, this is not going to ignite. I am not going to ignite in front of your very eyes during this presentation. I'm not. You can laugh. You can mock me, but I'm pretty certain that's not going to happen. It'll be an exciting video for YouTube if it does happen, but it's not going to happen. And the fact there's a critical heat flux is going to come out of this equation. And I could give this equation to pre-calculus students, and the exponential of a quantity is always positive. The numerator is always positive, but this denominator might be positive or zero or negative. And if this quantity is negative, there's going to be no ignition. All right, so if I was giving this to pre-calculus students, I wouldn't give them the question in this form, but basically we can analyze this equation and we can show there's going to be a critical value for L, and if L is bigger than the critical value, we can find a formula for the ignition time. So here's the formula for the critical value for L that students can find, and then they can find this formula for the ignition time. And this parameter for the ignition temperature, we're not predicting that value. That's something that the experimentalists will tell you, because they're irradiating their sample, and they're also measuring the surface temperature as a function of time. Like visually, you know when it's ignited because a flame appears above the sample. The formula of the ignition time, first order separable equation. So the game is we set the value for L and we measure the ignition time. It's saying that my connection is unstable, so perhaps I'll just try turning the video off. All right. The experimental is going to tell me the ignition temperature. H is the convective heat transfer coefficient. That's well defined for any given experimental configuration. S, you can't see now because I've turned my video off. That's the surface area that I'm irradiating. That's well defined. I know the ambient temperature. Epsilon is the absorbativity or the emissivity of the material. And if I don't know what it is, it's usually assumed to be equal to 1. So in this equation, I know everything apart from the heat capacity times by the mass. Or I know the mass because I can weigh the sample, so it's really the heat capacity. But isn't the heat capacity a known quantity? Well, in principle, you can measure the heat capacity for any material, but for new materials, the heat capacity might not be measured, so you might not know what it is. Secondly, the heat capacity changes with temperature. Now, a typical ignition temperature might be between 600 and 700 kelvins. Room temperature is 300 kelvins. That's a 300 to 400 Kelvin range. So when we think about heat capacity in this formula, it's really a representative value over the temperature range between ambient temperature and the ignition temperature. And this is what the bioscientist is interested in estimating, because he can then feed that into computer models for more complicated fire situations. It's an input value that needs to be known. So the idea is you do these small scale experiments to estimate the value for C, and then you can feed that into a more complicated model. As an aside, fire engineers are also interested in what happens after it's ignited. But our model's not to do with that. Our model's only to do with what happens up until it ignites. So yeah, so the real question is, what's the value for the heat capacity that best fits the data? So that's what we want to estimate. And what I do now is I ask students to use the critical value for L. They found an expression for it, and to rewrite the ignition time in this way here. Now, if I just go back to this blue formula, I know the value for L critical, and I know the value for L, and I know the value for the time to ignition. So it's easy to use a package like Excel to do a linear regression analysis on this function. But when this formula was first derived in the 1960s, there weren't that many computer packages to do linear regression. It was still quite common to do linear regression by hand using graph paper. A few of you might be too young to remember the days when linear regression was done using graph paper. So fire scientists wanted to get a slightly easier version of the formula. So now we can use Taylor series, because if the value for L is a lot bigger than the critical value, which that turns out to be a good assumption, I can use a Taylor series to approximate the log function. And now a student can derive this equation for the ignition time. So I'm going to plot the ignition time against 1 divided by L, and that's going to be the gradient. And I know everything apart from the heat capacity. So I've estimated the effective heat capacity. And in the fire engineering literature, they typically rewrite it in this equivalent form, and delta's in blue just for me to say that it's the thickness of the sample. So equation 10 is the one that fire engineers use. I did use this last year, and last year I didn't get around to getting students to do the linear regression bit. This year I'm going to get them to do the linear regression bit. And I might use this form of the equation instead. Actually, I might use this form as well, since we can use Excel or whatever package they like to do the regression using that form. So yes, I was hoping to have some data to show you and to show you the regression fits, but I ran out of time. But in the fire engineering literature, there's a lot of data that you can acquire for this kind of fitting, because it's been done quite often. Right, so that's kind of like the end of the module on here's an equation that we can give to students to solve, and it's got a real application in engineering. And in the remainder of the talk, I just want to talk about a few things that we can do with the equation. This is one of the ways that my students like to rewrite the equation. Now, I don't like using the word trick when I talk to engineering students, because it reinforces their prejudices about mathematics, but a common technique in first-year engineering mathematics is about multiplying by the number 1. And here, if I multiply by the number 1 and I write the number as a divided by a, I can see I'm going to have a common factor of a, and then I can bring this inside the bracket and I can rewrite the equation like this. If I rewrite the equation like this, then I can call this temperature here the effective, yeah, I think that should be the effective ambient temperature, but it is also the effective steady state temperature. So the effect of having the heat flux, it's equivalent to raising the ambient temperature. Now, why this equation is good is because my second year students understand the behavior of this equation without having to solve it. And so they can see, for example, that if the effective ambient temperature is below the ignition temperature, it's not going to ignite. And they can see that the critical value for the effective ambient temperature is going to be when it's equal to the ignition temperature. And then you can go backwards and substitute in, what was A and what was B, and then you can derive the formula for the effective heat flux. So this way of writing the equation is an intuitive way to understand the basic properties of the model. And maybe if I was teaching first year engineering students, I would give them the equation in this form to begin with. So up to now, I've been talking about the fact that the heat flux is constant, and in the cone calorimeter, it is constant. But people have been interested in doing experiments and models when the heat flux is not constant. And when the heat flux is not constant, I can rewrite my equation in this form. So we can see that this is going to be a linear differential equation, and it's going to be very easy to find the integrating factor. It's going to be an exponential function. And then it's going to, depending upon the function for L, it's going to be reasonably straightforward for students to integrate this equation. And people are mainly interested in the case when L is increasing or L is decreasing. And what's the reason for that? Well, in a fire, as the fire front moves towards you, the amount of radiation that's irradiated on you is increasing. So an increasing expression for L is mimicking the fact that as the fire front approaches, you get more radiation. Why might the value for L decrease? If you've got a material that decomposes and gives a lot of smoke, then the smoke layer is going to attenuate the heat flux and it's going to decrease the value for L. So what this means is that you've got a suite of problems that you could give to students by changing the value for L. And there's quite a lot of different values for L in the literature, and I just mentioned 2 of them here. An increasing power law, or to have the value for L decreasing at a constant rate. So to conclude, let me ask the question again. Can your students solve this differential equation? I was sure that my second year mathematics students could solve it until I used it as an exam question. And then I discovered that they weren't as good as integrating as they should have been. The equation actually looks like this, which looks more intimidating. But we can simplify this equation and we can rewrite it in that way. So we can solve the differential equation, but again, to paraphrase Winston Churchill, solving the differential equation is not the end of the process in a mathematical model. It's not the beginning of the end. It's merely the end of the beginning. And from our solution, we can do things like find as a critical value for L. That was quite handy for the military applications that motivated the work in the 1950s. And it's due to a basic fact that an exponential function can't be negative. We can find the ignition time as a function of L. And to do that, we use Taylor series. So it's nice to have an example where Taylor series is used. Maybe it's a trivial example, but it's nice to show students, oh, here's an engineering paper where engineers actually use the Taylor series to simplify a formula. And we can derive this formula and we can get data and plot it. And the data can show me 2 things. If I get a straight line, when I plot the ignition time as a function of 1 divided by L, I can estimate the effective heat capacity. If I don't get a straight line and it's curved, that means that my sample is not thermally thin. So that can be a useful conclusion to know. This is a useful parameter for fire engineers to know because they can use it as an input into more complicated models. Yeah, so just to repeat, linear regression analysis, we can get lots of data from engineering papers, and we can give the data to students. I still find that my students are shocked at the idea that in applied mathematics, when they're doing differential equations, they might need to do linear regression to estimate parameter values. There's lots of extensions for this kind of work. So I've been talking about a situation when you heat the top of a sample. You can turn your sample over like this, and you can heat it here, or you can heat it on both sides simultaneously, two-sided heating. We've assumed that the heat capacity is constant, but it really changes as a function of temperature. And typically people will fit heat capacity to a polynomial function in temperature. And here's the simplest one that they use. This is still going to give me a model that I can solve, because I'm going to have a linear function of t here, and this is a linear function of t. So I can use partial fractions and integrate. I've mentioned that the value for L could be a function of time. It opens up a new suite of problems to give to students. I've not mentioned how you extend the model to include radiative heat loss, but one common way to do that is just to say increases the value for H, so you keep the same model. And then all of these different things that I've mentioned here can be combined. So you've got lots of little projects that you can hand out to students. So let me repeat the message. The message is this, or it's a question. Can your students solve this differential equation? If they can, we can use this as a stepping door into a really simple problem in fire engineering, where fire engineers have used the solution of this equation to analyze data and to estimate an important parameter. And that concludes my talk for today.
Thank you.
We still have about like 3 more minutes. So like if anyone has questions, just feel free to ask.
Maybe there's no questions. I've got some references at the end. So this is the book that I mentioned by Barnes and Fulford, which is teaching differential equations through mathematical modeling using case studies. It was probably a little bit ahead of its time when it was first published in about 2003. If you want to know more about fire engineering and how fire scientists use these kinds of equations, this book by Dougal Drysdale is a good one, and I highly recommend it. And if you want to know more about the literature when people use non-constant heat fluxes, this paper's got a very good summary of the different functional forms that have been used and the papers that they've appeared in. And if you want to wait a little bit, we're currently writing up this talk. At that point. And thank you to Melissa and Beverly for your kind words.
You're welcome. I enjoyed this a lot. And I've enjoyed meeting you at last.
And Beverly did try and pull my leg this morning when she realized it was Saturday in Australia, and she asked me if I was talking from the future. And in return, I enjoyed pulling her leg by pointing out that Australians might think they live in the future, but they don't. It's you people on North America are sadly living in the past.
Quite a concept.
Well, if there are no questions, thanks everyone. I'll be ending this session. There's another one starting in like 5 minutes. So thanks everyone.
Thank you for coming.